Hello guys, today we'll be reviewing topic E.3 in the IB Physics HL Davis, which is radioactive decay. So let's first start with defining radioactive decay. Well, radioactive decay is a process in which an atom becomes stable. Okay, how does it become stable? Well, atom becomes stable is by decaying. In this course, we look at three types of radioactive decay. Okay, and this is why we call unstable atoms radioactive atoms. These atoms can decay, and you must know that decay actually can sometimes be very harmful to the human and be sometimes be fatal. So that's why we stay away from radioactive elements such as uranium and like that. That's why nuclear bombs or nuclear power houses are very unsafe to humans because they're all radioactive. Okay, so for radioactivity, we have three types of radioactive decay, or three types where particle decays to become more stable. These are three types. We're gonna start with number one, which is alpha decay. Alpha is a Greek letter denoted by this. Okay, so what is alpha decay? Well, alpha decay is simply when a atom, let's have a simple atom. I'll pull up the periodic table because I don't know the atoms, and you won't need to know, of course, the atoms. Or let's say carbon 12, and I think it has six protons, I think. Okay, so carbon 12 is here. Carbon is stable, but in this, or actually carbon, or I'll tell you later, but carbon here is stable, okay? So what happens? What is alpha decay? Well, alpha decay is described by the following equation where carbon 12, 6 becomes element X, 8 and 4 plus an alpha particle. So what happened here? Where carbon decayed into element X and lost 4 nucleons and 2 protons. So in total, it lost 2 neutrons and 2 protons. So what is alpha decay, or what is the alpha? We like to call this the alpha particle, but actually, the alpha particle is something important in chemistry and physics. An alpha particle is simply your helium nucleus. It is simply an helium atom without the electrons, so the nucleus, of course. So if you look, helium is actually also 4 and 2, consists of two neutrons and 2 protons and electrons, but this nucleus, of course, doesn't have electrons, so an alpha particle is actually simply helium. Since we neglect actually the mass of the electrons, we say that they're equal mass and they're the same, okay? So when a particle is not stable, it emits an alpha particle, meaning it loses 2 protons and 2 neutrons. And in total, in order and for questions like these, you always have to know one thing, that the conservation of neutrons and protons, so there's conservation of the mass number, which is these here, and the conservation of proton number. So on one side, both sides, the number of protons and the mass number must be equal. If not, you're doing something wrong. Okay, this is the more simple decay. There's nothing to talk about, but later I'll tell you it's part of a bigger picture if you want to say. But let's go on to the second type of decay, which is denoted by beta decay. So actually, there are two types of beta decay: beta plus and beta minus. The beta minus is more, you'll see it more, it's more occurring in nature, but I'll show you what it means using carbon again. So carbon 12 and 6 goes and it becomes carbon 12, it remains the same atom, but carbon 7 plus an electron, or sorry, yes, an electron and something I'll tell you about here. Okay. So here, this is getting confusing, I know. But what happened? Okay, this we're talking about beta minus. So let's start with beta minus, the one that you see more. A carbon becomes another carbon atom. It becomes another carbon isotope. Oh, sorry. It cannot. What I said is completely incorrect. It becomes another atom here, and I'll tell you why. Or it becomes another element because the number of protons is different, and that means that they're different elements. But what happened? Well, simply, if you look at it, a neutron became a proton. As you see, the number of protons increase, but the mass number remains the same because protons and neutrons are part of the mass number. So it doesn't matter if it's a proton or a neutron, the mass number will remain the same. But it also emits an electron, and the electron, of course, cannot exist within the nucleus, so it is emitted out of the atom. It's ionized, if you want to say, and something we call an antineutrino. You don't need to know much about the antineutrino. Antineutrino is a particle with very small mass, like it's almost zero, we like to say. And it was hypothesized since that some energy was lost here. So the neutron's energy uh, or some energy was left over. So that energy had to go with something, or it would violate the law of conservation of energy. So this particle was created, and this particle takes most of the energy of the decay, and it moves at very fast speed, very close to the speed of light, since it has very low mass. Okay, and we like to call it antineutrino because it's the anti-particle, if you let's say. So I'll introduce you to this. So you don't really have to know it, but all particles have their antiparticles. So a antineutrino is the antiparticle of the neutrino. The difference between them, you don't have to know, but when talking with particles with charge, they only have to know that particles and their antiparticles have opposite charges, but the rest of the things you don't have to know. So in our syllabus, neutrinos and antineutrinos are almost the same, but you have to be able to draw them. So an antineutrino is drawn by this V with a dash, and I'll show you how the neutrino is drawn. And I would like you also to know that when an antiparticle and a particle collide, they turn into energy. They completely energy, and I'll tell you why when I finish the introduction to these decay processes. So let's move on to the other type of decay, beta plus. Using carbon, it actually becomes this plus. So you see here, everything has become opposite. A proton in this case became a neutron. As you see, the proton number decreases, but this will always stay the same in beta decay. A positron, and if you focus, you know that this is the anti-particle of an electron, so it has the same properties but opposite charge. And the normal particle, the neutrino, actually, this is the neutrino, not the anti-neutrino, and you have to be able to draw them, as I said. So the anti-neutrino is with a dash, the neutrino is with no dash, it's a V with no dash, and of course the electron and positron exactly the same, but you just opposite charges. Okay. uh, Now I'll go on to the final decay, which actually has no equation. It's easier than this, and you simply have to know it. So this actually usually occurs after beta decay. So let's use beta decay first. So this decays to some carbon atom, beta plus, let's say, some atom plus a positron plus something. But somehow this element X has leftover energy. So what does it do? Well, leftover energy means it's unstable, right? So it wants to become stable. But since we're talking about energy, it doesn't want to emit something with mass, or it doesn't want to emit a proton, neutron, or electron. It wants to just emit that extra energy. Well, that extra energy is emitted in form of gamma rays. And if you know what gamma rays are, they are part of the electromagnetic spectrum. So gamma decay is simply the emission of a gamma photon or gamma photons, and they're shown gamma. This is the Greek letter gamma. So for gamma decay, you're literally writing it like this. So if this were to decay alone without beta, it would become the same atom exactly, and you would just add some the gamma. Okay. So usually gamma decay follows beta decay. You'll find that, but there is no change in the element itself. The only thing that changes is the energy of the element, since gamma particles or electromagnetic waves, so have no mass, only energy. Okay, so now the important part of this, all of this, is actually something more important. We talked about in the last video how atoms at discrete energy levels, and we showed how each energy level has specific energy, exact energy, represented by an integer. So actually, both two of the following decay processes actually shows that the nucleus itself also has energy levels. Can you tell me which one? Well, if you were focusing, you'd know that there would be alpha and gamma. Why? Well, alpha decay is the emission of a helium nucleus every time. Nothing will ever be different. If it's alpha decay, it's the emission of two neutrons, two protons, nothing else. It is always continuous. So we could say it's discrete, right? We could say that the emission of that specific nucleus is discrete. It never changes. The same for gamma. Gamma decay, you're always emitting a gamma photon of the exact frequency, exact wavelength, and of course they all move at speed c. So we could also say it's discrete. But for beta decay, well, that's not the case for both types of decay, since the neutrino's energy, the anti-neutrino or the neutrino's energy, can vary. It's continuous. The particle was actually created to explain that they are not discrete. They are actually continuous, and these particles were created to explain their continuity. Okay, so if you're asked to say which decay processes provide evidence for discrete nuclear energy levels, you would state that they are alpha and gamma decay only, not beta decay. And if said to explain, you'll just say what I exactly stated here. And this is something very important you need to know about radioactive decay in general. So, uh, another thing that is very important in radioactive decay. Radioactive decay actually releases energy. Uh, or let me write down the equation first. This is the equation I know many of you know. It's Einstein's mass energy equivalence equation. E equals mc squared. So, when radioactive decay occurs, so when a carbon atom emits the alpha particle plus some alpha particle, yes, it becomes so it becomes, let's say, use carbon again, it becomes some element 8, 4 plus the alpha particle, which is 4 and 2, and thus it's conserved, right? But actually, it releases some energy. The mass of these, okay, is greater than the mass of this. So some energy must have been released, or some mass have must been released. But when scientists looked, they can't find any physical mass that can explain this. So the only way that Einstein could explain this is that that mass was converted into energy, and that energy was released. In order to find that energy, we take the mass difference between all three of these and multiplied by the speed of light squared. And that the mass difference between them is known as the mass defect. And that mass defect is the mass that has been converted into energy through the radioactive decay process. Okay? So if asked to get the energy released, you'll use this equation. If asked to get the mass and given the energy, you'll rearrange it and find the mass defect. And the mass defect is, as I stated, the difference between these two masses. Okay, and it has to be a positive value. Uh, so if you get a negative value, just switch it or and show it's positive. So the mass defect is the mass difference between the products and the reactants, or any way you want to say it. Okay, this is a fundamental paradigm shift, actually, you could say. since it helped us understand how mass and energy are the same actually. And all mass is energy and all energy is mass, and they are related by this simple equation. They are directly proportional since the speed of light is a constant, a universal constant. Yes, so you'll be asked a lot to use this equation, and it's very fairly simple. Now I'm gonna move on to the the concept of radioactive decay itself, not or I'll I'll move on to how decay occurs or equations that explain decay. So I'm gonna first start with that decay actually can occur over very short periods of time or very long periods of time. So uh, some elements decay in mere seconds while some decay in millions of years. Okay? So the following equation I write describes how the number of atoms of a certain element, of number of nucleons or a certain element, is directly proportional to the initial number of nucleons by Euler's number. Or but I'll tell you, I'll just write it down. So n here is the number of nucleons at a given point in time. N node is the initial number, which you'll be given, multiplied by Euler's number e to the negative lambda t. So t here is time, so you know it. But what is lambda? And of course, negative, if you take math, you know that negative e to the negative something is exponential decay. And since here we're talking about decay, then this negative shows how radioactive decay decays exponentially. Okay, so what is lambda? Okay, lambda is actually something very important and very complex, but I'll tell you its definition. Lambda is the probability that a decay will occur per unit time. So you can get lambda in days, seconds, hours, doesn't matter. What matters is you give your answer in the right units. Okay? And actually, lambda, well, I'll tell you something. So actually, we also like to know the half-life of a certain element. Okay, what is the half-life? Well, simply the half-life is the time taken for for n node to be equal to n node over 2. So the number of nucleons halves. This is what the half-life means. This is the time taken for the following equations. So let's say, so for the half-life, we want n to be equal to n node over 2. So simply it becomes n node over 2 equals n node e to the negative lambda t. And if you cancel both sides, so you're simply solving for half equals e to the negative lambda t, right? So you want to get rid of the negative sign while you actually do this. So it becomes e to the lambda t. And you want to get rid of the exponent, right? So you ln both sides and it becomes ln 2 equals lambda t, and lambda equals ln 2 over t. So t here, we're talking about the half-life for the time it takes for the number of nucleons to half. You have to know that the half-life is that definition is that. And thus we've derived the equation. Actually, the relation between the decay constant and the half-life is this. You can also write it as t half equals ln 2 divided by lambda, which is the decay constant. Okay, so this is very important to know. It's in your data booklet. It's actually the final equation in the data booklet. But also, we could also describe radioactive decay by what's known as activity. Well, activity is simply how many decays are occurring per unit time, not the probability of decay. Don't get it confused, but activity is how many decays occur per unit time, so the rate of decay simply. And activity can be expressed by two equations, or actually several equations, but I'll show you all of them. Two of them are in data booklet. The third one actually is the most useful, and I'll write it down for you. So it states that the activity of some radioactive element is equal to lambda n. Well, we know n equals n node e to the negative lambda t, so it simply becomes lambda n node e to the negative lambda t, where we all know that lambda is the decay constant, n node is the initial number of nucleons, e is Euler's number, and t is the time, or the time where you want to get the activity, okay? But this can also be written as the following equation. So let's state we want the initial activity. Well, the initial activity is simply equal to lambda multiplied by the initial number of nucleons, right? So what if we substitute this for this here? So it simply becomes that the activity is equal to the initial activity multiplied by e to the negative lambda t. And we see how the relation between the initial activity at a given point in time and the initial activity is the same with the initial number of nucleons, or the number of nucleons to the initial number of nucleons at a given time. So they both are actually exponentially, and they decay exponentially, okay? So now that I've explained, let's solve some questions, okay? A sample of pure iodine decays into xenon with half-life of 8 days. Okay. What is the number of iodine atoms remaining divided by the number of xenon atoms formed after 28 days? So 28 days is 3 half-lives. So let's say the number of xenon atoms is n. So it becomes n over 2 to the power of 3, which is simply n over 8, okay? So this is the number of xenon atoms. Well, uh, that this is the number of iodine atoms remaining, okay? Not the number of xenon atoms. The number of xenon atoms is simply what's remaining, which is 7n over 8. So n over 8 divided by 7n over 8, if you write it down, divided by 7n over 8 is equal to 1 over 7. These cancel out, and this becomes 1. So it becomes 1 over 7, which is the correct answer. When a nucleus of nitrogen, protein 7, is bombarded with alpha particles following the nuclear reaction can occur. So bombarded by alpha particles means you basically added the alpha particle to it. And here you write it down, plus some x. So let's add here. Well, if you want to see here, you look here and you see, let's see if both sides have the same amount, conservation of mass number and conservation of proton number. So this side is 18 and the other side is 17. So 18 equals 17 plus x. And down here you have 9 equals 8 plus x. Right? So what particle has a mass number of 1 and a proton number of 1? Well, that is simply a proton. So the answer is B, which is a proton. And this is very easy. You don't even need it to be multiple choice. You'll know it very easily. Oh, yes, I wanted also to show you something else explanation. There is something known as the stability graph. It shows how stable atoms are, okay? And I'll explain it to you now, okay? The stability graph shows something like this, okay? It's something like this, but there are some curves down here. So here are the least stable atoms, and at about this point is the most stable atom, which is, you have to know it, is iron, Fe. So iron, being the most stable atom, will never decay. It is the only atom or element in the periodic table that has no decay constant. The probability of a decay occurring is simply zero. Why? Well, decay occurs to become more stable, but if you're already the most stable element, why would you decay, right? And actually, fission and fusion also occur in order for an atom to be more stable. So iron is simply the only element that does not decay, have fission or fusion, since it does not need to be more stable. It's already the most stable. And this part to the left of iron is where fusion occurs. These smaller elements bind together to create larger elements until they reach iron, where it's the most stable. And the other side, you have fission. Well, these bigger elements break down into smaller elements in hopes of being more stable or closer to iron, right? And yes, so thought I would show you that. It's very important here. So the initial number of atoms in a pure radioactive sample is n. So let's write it down. The radioactive half-life of the sample is defined as time taken for one atom to undergo decay. That's incorrect. Probability for n over two atoms to undergo decay. Well, that's like a mix between the decay constant and the half-life, so it's incorrect. Time taken for n over two atoms to undergo decay, which is correct. Okay, which one of the following statements is true for the decay of a radioactive isotope? The activity at any particular time is directly proportional to the original number of nuclei present. Well, you cannot actually say that. Why? Well, if you write down the equation in data booklet, it's lambda n node e to the negative lambda t. Okay? So, since lambda is not something that's constant, uh, you can't say that's directly proportional. You can say it's directly proportional for a constant lambda, but not for any value of lambda. So A is wrong. The activity at any particular time is proportional to the number of nuclei of the isotope present at that time. Well, yes, A equals lambda n, which is correct. A detector placed to a radioactive source detects an activity of 260 BQ. I want you to know that the unit for activity is known as becquerels and denoted by a large B and a small q. So A node equals 260, and that's the SI unit for it, okay? The average background radiation at this location is 20. So the actual radiation coming from the isotope is 240, okay? The radioactive nuclide has a half-life of 9 hours. What is the activity detected after 20 hours? So let's just remove their background activity, then we'll come back to it later. Well, 36 hours is 4 half-life, so we're basically dividing 240 by 2 to the power of 4, which equals 15. Well, he's asking you what is the activity detected. So he's not asking you about the activity of the radioactive isotope only. He's asking you about the activity in general. So you have to add back the background activity, which is 20. So it becomes 35. And it is the right answer. The radius of nucleus can be estimated from experiments involving the scattering of charged particles, which is correct, which is the Geiger-Martin experiment, where they threw alpha particles at a gold foil and tried to estimate the radius of the gold nucleus by increasing the energy of the alpha particles until it is deflected to 180 degrees back. That is when you know that it has reached the closest range it can. So it can be estimated. The average binding energy per nucleon of an oxygen nucleus is 7.5 mega electron volts. What is the total energy required to separate one nucleus of oxygen? Well, oxygen consists of 15 protons and 18 electrons. So binding energy per nucleon is not the energy required to separate a nucleus. The binding energy in total is what you need. So we're simply multiplying 7.5 by the number of nucleons, which is 15, which gives us about 113 mega electron volts, which is the exact energy required to separate one nucleus of oxygen 1518. Let's find another question. The half-life of a radioactive element is 5 days. A freshly prepared sample of 128 grams of this element, so n node equals 120. And don't worry, you can actually use mass here since it's proportional to the number of moles and particles. So It doesn't matter actually. After how many days will there be 16 grams left? So he's basically telling you 16 equals 128 over 2 to the power of some value x, which is the number of half-lives. Okay, so the number of 5 days. So if you get x, you know how many days. So let's just rearrange. Well, you can actually solve it here, but 16 is equal to 128 divided by 8, actually. So what 2 to the power of what is 8? Well, 2 to the power of 3 is 8, so x equals 3. But that's not the answer. The answer is the number of days, not the number of half-lives. Well, the half-life is 5 days, so we multiply this by 5 equals 15 days, which is the correct answer. Given that uranium has a half-life of 4.5 times 10 to the 9 years, what is the probability that a particular uranium atom will have decayed after 9 times 10 to the 9 years? So he's basically telling you what is the probability of decay after 2 half-lives. Okay? So simply, they're apportioned by ln2, so you're using the equation that the probability of decay is simply ln2 divided by 4.5 times 10 to the 9. Given that U has a half-life, particular atom will have decayed after 9 years. Let's leave this question for later. Okay, sample contains radioactive substance with a half-life of 3.5 days, so T half equals 3.5. After 2 weeks, the fraction of the radioactive substance is decayed, so 2 weeks is 4 half-lives. So 4 half-lives have occurred, so let's let the original number be n. So it becomes n over 2 to the power of 4, since that's the number of half-lives, would become n over 16, okay? Well, n over 16 here is expressing in percent. Let's 1 over 16 is approximately 6%, so that's the correct answer. What statement about alpha particles, beta particles, and gamma particles is true? Gamma radiation always travels faster than beta particles in a vacuum, which is the correct answer. Gamma particles are photons, so they travel at the speed of light, meaning they are faster or equal to the speed of anything. Okay, a nucleus of potassium undergoes beta decay to an excited state of a nucleus of argon. The argon then reaches its ground state by the emission of a gamma photon. The diagram represents the beta plus and gamma energy, okay? What particle represented by the letter X? Well, if you know the beta decay, it emits three things. Or beta plus decay, it consists of three things: a proton becoming a neutron, and the emission of a positron, and the emission of a neutrino. Okay? So the answer is here, and neutrino is what takes the energy. So the answer would be the neutrino, which is what takes the energy. Okay, a uranium-238 92 undergoes an alpha decay. X plus, let's say, alpha for 2. What is the number of protons and neutrons in the resulting particle? Well, the conservation of mass number, this would be 234, and this would be 90. So number of protons is 90. What? Oh, it's followed by beta minus decay. Okay. So it becomes this, and then beta minus decay, we're focusing about this main product. So beta minus means the number of proton, a neutron becomes a proton, so it simply becomes 234 x again, and this becomes 91. So it has 91 protons and 234 minus 91 neutrons, which would become 143. So the answer would be C, which is 91, 143. Consider a sample of radioactive isotope with unstable nucleus that undergoes alpha decay. The sample initially has 1 times 10 to the 20 nuclei. So it's times 10 to the 20. And its half-life is 3 hours. So you might want to change this to SI units, but we'll wait for now. Explain the role of the strong nuclear force in the stability and describe why alpha occurs as stated. Okay, so the stability actually of the role of a nuclear force is that it actually uh, it actually holds the nucleus together because protons have charge and all have the same positive charge, so the Coulomb force between them repels them, and that force always increases as the number of protons increases. So something has to keep the nucleus together, and that's what the strong force do. It keeps the nucleus together, and if the Coulomb force starts overcoming the strong force, the atom automatically decays, because if that would occur, the nucleus technically would explode due to the outwards force due to the Coulomb force. So that's the role of the strong nuclear force, okay? Okay, let's solve the final question for today. Okay, a proton, an electron, and an alpha particle are at rest. Which particle has the smallest magnitude of ratio of charge to mass, and which particle has the largest magnitude of ratio of charge to mass? Well, it's very simple. Smallest charge to mass ratio is the alpha particle, since it has a charge of 2, but the mass of 4. Okay? And the largest would be an electron, since it have a very small mass, but the same charge as a proton, so the answer would actually be A. So today we reviewed topic E.3 of radioactive decay. I explained the laws of radioactivity, the types of radioactive decay, and their roles in keeping atoms stable. Thank you.